Hello students, this is the second part of the lecture. So we already went over these graphs, right? So see, so they are discussing these points. Let us see. To the left of point E in section B here, what is happening? You see that the marginal product curve, the dark blue line, is below the average product line, which is the light blue line. So at this to the from here on this side, what do we have? For every level of labor, you will see that marginal product of labor is lower than the average product of labor, right? On the other hand, to the left hand side of that point E, we have what? The dark blue line, marginal product of labor, is higher than the average product of labor, the right blue line. See that? So this is higher vertically. You see that distance higher, and on the other hand here, look at that vertical distance between the two curves. Marginal product is lower than the average product curve. See? So this is because you see at E, the E is the point of intersection, right? So if this is the marginal product, then we know this is the average product curve. So marginal product curve is coming from above. This marginal product curve is coming from above and intersecting that average product of labor curve at its highest point. So that E is the maximum of the average product of labor. See? So the reason is that what? That marginal product is actually the driver. See? On the left hand side of E, on this side, right? On this side, so on this side, before over this area, when marginal product increasing, it will pull the average product up. So now marginal product higher than average product, so it is pulling the average product curve. And look at that, average product curve is increasing. See that going up. On the other hand, this is the maximum point where they intersect. They are equal at that point of intersection. Marginal product equal to average product at that highest point. But to the right hand side in this area, look at that. Marginal product is smaller than the average product, and it is taking the average product down. See? So that is why the point of intersection is the highest of the average product of labor, right? Okay, so and now, so this is what they're saying, what we have discussed. In general, the average product of labor is given by the slope of the line drawn from the origin to the corresponding point on the total product curve. So see, this line we call is what? Ray. Slope of the ray drawn from the origin to that point, right? And on the other hand, marginal product is product of labor at a point is given by the slope of the total product at that point. So this slope we measure with a tangent, right? So slope of the tangent then gives us marginal product. This is tangent, as we have discussed also before in that slide, right? In that graph. Now the relationship between marginal and average product, as we have said, marginal product will decide whether average product will decrease or not. If marginal product is higher than the average product, right, it will pull up the average. So average product will increase. On the other hand, if marginal is below the average, right, this is happening to the right hand side of that point E. If marginal below the average, right, then what happened? It will pull down the average product also itself, and that is what they are explaining in here. See, figure 6.1a, when the marginal product of labor is greater than the average product of labor will increase. On the other hand, at point C, the average and marginal products of labor are equal. And then finally, as we move downward beyond C towards D, the marginal product falls below the average product. Marginal product falls below here from C to D. Look at that. If you look at this graph, it becomes clearer, right? Okay. And also if you look at that point C, this one corresponds to point E, the maximum of the average product curve. See, look at that tangent, look at that tangent OA, that tangent ray of that tangent ray of that line is the highest. If you draw other rays from origin to that point of total product, all those rays will have what? Lower slope than the ray at point C. So that is why average product is the slope of the ray is highest at point C. See, look at that. This is the maximum. Now let us go to the next slide. Law of diminishing marginal return. This principle that the use of an input increases with other input fixed, right? As we in this example, as we use more and more of labor with a fixed amount of capital, the resulting addition to output will initially increase, reach a maximum, but beyond that it will decrease, right? And this is what happened here. If we go back to the table, look at that. Here, look at this marginal product. See, look at this. Let me make some room here. So look at that. So what is happening here? We are using more and more labor, right? But amount of capital remain fixed. So initially marginal product is increasing, right? But then it will what? It start to decrease. So this is the maximum. Beyond this, marginal product is start to decrease. Here it reaches zero, and beyond that becomes what? Negative. Too much crowded, overcrowded, congestion, right? Workers cannot work. Too few machine tools equipments, right? So that is why. This is the law of diminishing marginal return. In the short run, law of production is governed by this law of diminishing marginal returns, right? Then now let us take a look at figure 6.2, the effect of technological improvement. So what happens, this is where we start O1, this is point A, right? Labor productivity output per unit of labor can increase if there are improvements in technology. See, so the same worker now, because he is using specialized tools, improved tools, he can now produce more. And this is shown by a shift of the total product curve. Technological innovation will move that Q1 total product curve to Q2. See, compare A and B. If you compare, you will see that the workers can produce more. Average product of labor is higher at B than it is at A. Similarly, if there is more technological innovation, the total product curve will again shift from O2 to O3, and that C is telling us that workers on an average can produce more than workers were producing before at B on O2. See, every time there is technological innovation, for the same worker out, they can produce more, then the curve will shift up in this direction, as we have shown to you, right? Same worker are producing more and more. Now what about this example? Let us see a production function for healthcare. Do increases in healthcare expenditure reflect increase in output, or do they reflect inefficiency in the production process? So let us see. The United States is relatively wealthy, and it is natural for consumer preferences to shift toward more healthcare as incomes grow. However, it may be that the production of healthcare in the United States is inefficient, right? So let us go to the graph and explain how this can happen. A production function for healthcare, additional expenditure on healthcare inputs increase life expectancy output along the production frontier. See, this is input expenses, and this is what increased life expectancy. This is input expenses in healthcare, right? Points A, B, C. Points A, B, and C represent points at which inputs are efficiently utilized, right? But along there are diminishing returns when moving from B to C. right? So look at that, B2C marginal product is decreasing. Look at the slope. If you draw the slope, or from A to B, right? You increase that expenditure increases, output will increase, but that increase will be what? Output will increase, but that increase will be lower than the before. So which is reflected by the slope. Remember, slope of this tangent is the marginal product of labor, and marginal product of labor is decreasing because slope, look at that slope, tangent of this slope is decreasing. The slope become flatter and flatter. And now, although there are diminishing returns when moving from B to C, point D is a point of input efficiency. This E in this graph, in this setup, is inefficient. Why? Because look at that. With this amount of expenditure, the life expectancy, the frontier, the mm, uh, is telling us that it should be maximum should be B, but it is what? At D it is lower than that. Not 7, increase in life expectancy 6. So here you spend the same amount of money, right, but get only 6 additional years of life expectancy instead of 7. So in this graph, any point here below, right inside, which is falls below this frontier, right, is inefficient. Now, what about this Malthus and the food crisis that he predicted? Malthus was a famous statistician, Thomas Malthus, 1766 and 1834, and he predicted that world production of food will not be able to match world production of growth rate of population. See, and Malthus predicted that as both the marginal and average productivity of labor fell, there were more mouths to feed. Mass hunger and starvation would result, right? That is what he predicted, right? So they are saying that Malthus said that we only have a limited amount of land, and when we are using more and more labor with it, production will be subject to diminishing law of diminishing marginal return. As we apply more and more labor to the fixed amount of land, output will increase, but what? It will initially, but then it will stabilize, reach a maximum, and beyond that it will start to decrease. And if so, then for sure Malthus predicted that world production of food will not be able to keep pace with world production of population, right? And as a result, he predicted mass hunger and starvation. But Malthus was wrong, although he was right about the diminishing marginal returns to labor. So what happened? Over the past century, technological improvements have dramatically altered food production in most countries, right? Including developing countries such as India, because there is what? Now agriculture science has developed. There is hybrid seed, right? There is GMO, genetically modified seed. They are weather resistant, more pest resistant, right? So output is higher than ever before, right? As a result, the average product of labor and total food output have increased, not decreased. So if you take a look, index of world food production per capita, take a look at this. 1948-52 was 100, and all this time, right, 2009 is what? 155. See that? The hunger remains a severe problem in some areas, in part because of the low productivity of labor there. But uh, we have what? Because thanks to this technological improvement, that we were able to avoid this mass hunger and starvation predicted by Thomas Malthus. He did not see the role that technology will play. So this is the role. See, innovation. Because of this innovation, the curve is shifting up with the same labor as before. Look at that. You can now produce more. Before you are producing this, now you can produce more. Or before you are producing this on this O2 curve, now same labor can produce more. See that? So Malthus and food prices. This is figure 6.4. Cereal yields and the world price of food. What happened? 1970 to 2010. World price of food index. Look at that. This food or price index relatively stable, right? Over time, there is an tendency to increase from 2005 to 2010. But what about cereal yield? Look at that. Cereal yield is continuously increasing. See that? Because of this continuous increase in more food available now, right? And this was made possible by what? Innovation and technology. Now, labor productivity, as we said, average product of labor, APL, right? So total output divided by total labor, that is output per worker, that is average product of labor. Now, for an entire industry or for the economy as a whole, we call it labor productivity, right? So industry means that you take the output Q of the entire industry divided by labor employed in that entire industry. So that is average product of labor for that industry, or we can do it for the economy as a whole. Productivity and the standard of living. Consumers in the aggregate can increase their rate of consumption in the long run by increasing the total amount they produce, right? They produce more, then they can consume more, right? So consumption amount increases. Understanding the causes of productivity growth is an important area of research and economics, because this means that if consumption per capita can be increased, welfare of the standard of living of the people, welfare of the people can increase. We do know that one of the most important sources of growth in labor productivity is growth in stock of capital. Capital plays a vital role. See, labor has to work with capital to produce output. So if there is sufficient stock of capital, labor can then produce more. And if there is innovation, the same improved machine tools equipment can produce more with the same labor, then that is even better. Now, stock of capital, total amount of capital available for use in production. See that? Total amount of capital that is available in a machine tools equipments, how much machine tool equipment, production plant, right, robots, and all the other facilities a country has at a certain point of time. That is the stock of capital. And the technological change, development of new technologies, right, allowing factors of production to be used more effectively. The same labor can be what? Can now produce more because of new technology and innovation, new method of production, right? Science has paved the way in this case. Now, what about labor productivity and the standard of living? Will the standard of living in the United States, Europe, and Japan continue to improve, or will these economies barely keep future generations from being worse off than they are today? Because that the answer depends on what? Several things. Because the real income of consumer in these countries increases only as fast as productivity grows, the answer depends on the productivity of workers, how much each worker can produce, because then they can consume more, and they consume more, then the more they consume, the higher is their productive standard of living. So let us see, this is a figure, labor productivity in developed countries, right? 1960 to 73 to here 2001 2009. So look at that, GDP per hour one in 2009 dollars, US is 56, Japan 38, France 54, Germany 53, and United Kingdom 45. See that? And annual growth rate of labor productivity. So let us concentrate on the later years. Is in the US 1993 to 2000 is 1.94. Here it is 2001 to 2009 is 1.90. Here this is what United Kingdom was 2.22, but then it fell to 1.30 for the 2001-2009 period. See, and in all the other countries, especially in Germany and France, look, 0.9, 0.8 for this period, right? Later period, which is much smaller than the US and what? And Japan. So far we have discussed production with one variable, right? Labor, and the other variable capital remain fixed. Now production with two variable inputs. So first question concept we will introduce is ISOQuant to analyze decision of the firms. And in this situation, when two variable inputs two variable inputs, when all inputs are variable, right? So capital and labor both variable. There is no K bar here, right? So ISOQuant, these are curves showing all possible combinations of input that yield the same output. See, Q is output. So all combination of capital and labor that will yield the same output Q. So here we have labor, here we have capital, and look at that. To produce 75 units of output, you need either 5 capital and 1 labor, or 3 capital and 2 labor, or 2 capital and 3 labor, or what? Or 5 labor. See, all will produce what? All of these will produce 75 units of output. So this is what the ISOQuant shows. ISOQuant will show us all the different combinations of inputs, right? In this example, labor L, capital K. All the combinations of capital and labor that produce the same unit of output. Then we will show you soon. What about ISOQuant maps? ISOQuant map graph combining a number of ISOQuants used to describe a production function. So this is actually the graph of a production function. Look at that. Let us concentrate on Q1. Q1 is showing us 55 level of output. And how can we produce this 55? We can either use this A, right? 3 units of capital, 1 units of labor, or you can use this D, 1 unit of capital and 3 unit of labor. See that? All is 55, right? So all the other combinations, if you can pick, they did not, but if you can imagine, give us the same 55 units of output. See that? Okay. So that is ISOQuant Q1. That is the ISOQuant for 55 units of output. What about the ISOQuant for 75 units of output? So you can combine this B or here or here. I'm just giving you more examples, right? All of those different combinations of labor and capital, right, will give you the same amount of output. On the other hand, then Q3 is for 90, right? So that E and C, those two, and all the others, right, that we are not mentioning, can produce that 90 units of output. So ISOQuant, this is just a locus of point. Every ISOQuant is a locus of point that will show us the what? That will show us the different combinations of the two factors plotted, right? Labor plotted on the horizontal axis and capital plotted on the vertical axis, right? That shows the same level of output. So for Q1 it is 55, for Q2 is 75 units of output, for Q3 is 90 units of output. By drawing a horizontal line at a particular level of capital, say 3, we can observe diminishing marginal returns, right? Reading the levels of output from each ISOQuant as labor increased, we note that each additional unit of labor generates less and less additional output. See? So let us say they are saying that if we draw a horizontal line like this 3, and then we observe diminishing marginal return because every unit of output, reading the level of output from each ISOQuant labor is increased. So labor here is for 1 unit of labor we are producing what? 55. For second unit we are producing what? 75. For the third unit we are using what? 90, we are producing 9 units, see that? So we are changing labor in this way, and what, and we are changing labor in this way, and that is how our output is also then changing, right? If we now calculate marginal product of labor for each of those changes, so change in output Q, change in labor. So for this change in labor, the first unit, right, output change increases from 0 to 55. So marginal product of labor here is what, 55. On the other hand, for the second unit, for this unit, right, what happens? Marginal product from A to B, which is marginal product of labor. Now A to B, B is 75, A is 55. So 75, so it's 20, see, 20 increase in output. Then what about the next one? The third unit, right here, third unit here, output increasing 75 to 90. So yes, so its marginal product for this from B to C is what? Marginal product of labor is 15, right? That's okay because we are keeping capital fixed here, right, at 3. So you see, this is how we can confirm another way to confirm the law of diminishing marginal returns. Now the next thing, we talk about input flexibility. Isoquants show the flexibility that farms have when making production decisions. So you see, this means that there are different ways to produce the same amount of output, different combination of labor, right? They can usually obtain a particular output by substituting one input for another. So here you see we are substituting one labor with capital, then another labor, then another labor, another unit of a labor. So what happens is that here they are saying like this. So this is labor, this is capital, this is 0, this is isoquant IQ, right? Here you can produce that unit, say IQ for 55 units, right? With this combination, or you can produce the same output 55 with this combination. You are using less capital and more labor between these two points. See, they can usually obtain a particular output by substituting one unit for another. This is calling flexibility, right? Now, diminishing marginal returns, even though both labor and capital are variable in the long run, it is useful for a farm that is choosing the optimal mix of inputs to ask what happens to output as each input is increased, with the other input being fixed, right? So that is when even in the long run we may need that, we need to keep one fixed and then find out what is happening to the other, as we did here, right? Even in the long run, this one we keep capital fixed at 3 units, and then we examine marginal product of labor here. Now substitution among inputs, right? Marginal rate of technical substitution is MRTS, as we call. So this is the rate at which one input can be replaced with another input, right? One extra unit of labor can be replaced by sacrificing some capital but still produce the same output. Amount by which the quantity of one input can be reduced when one extra unit of another input is used, so that output remains constant. So we are on the same indifference curve. So sorry, isoquant curve, right? So MRTS let us now define as change in the capital input divided by what? Change in labor input, right? So delta K over delta L for a fixed level of Q, right? Now diminishing MRTS, marginal rate of technical substitution, additional output from increased use of labor. So see, marginal product of labor and change in labor. Labor increases L, and because when we increase labor by delta L, how much will output change? We write it as MPL. This is the change in output associated with one more unit of labor. and this is the change in labor, right? You multiply them, you get output, additional output. And now reduction in output from decreased use of capital. So as we said, we are increasing our labor but decreasing capital. And how much will output fall when we decrease capital by delta K? To know that, we have to multiply that by del M, marginal product of capital. See, delta K is telling us how much capital we decrease, and that marginal product of K will tell us how much output will decrease if we reduce one more unit of capital. And then when we multiply, then that tells us how much output will decrease when we decrease capital by delta K. Likewise, this one, MPL multiplied by delta L, will tell us how much output will decrease when we decrease labor by what? By delta L. And then we know that we add these together, gain in output because we increase labor, loss in output because we decrease capital is 0 along the same isocont, right? Along the same isocont, remember output remains the same. So when we are moving from one point, right? So this is labor 0 and capital. This is isocont, right? When moving from this point to this point, when we are using what? When we are reducing capital and increasing labor, what happens? Right? Okay. Now, now that is output remains the same. Just this change in Q is 0. Output does not change, right? Here. So now we simplify this. From here we get marginal product of labor divided by marginal product of capital equal to minus delta K delta L equal to AMRTS, marginal rate of technical substitution. See, that is what it shows us. It shows us how much, it shows us the ratio of the two factors of production, MPL divided by MPK. Here there will be a divide sign, and this is the opposite. This is negative of the slope of the isocont. See delta K, you see we are plotting K here, we are plotting K on this axis, this is L. So delta K is delta L is rise versus run. So this is the slope of the isocont, right? So it means that tangent, right? The isocont is a curve. So if you want to measure slope of that curve at a certain point, you have to do, you know that you have to draw a tangent, right? This one. So I want to measure slope. I draw a tangent. Slope of that tangent now here is delta K. We have K in this axis, right? 0 and L. This is delta L. So MRTS, marginal rate of technical substitution, is what? Delta K delta L, and which we have shown is also equal to this ratio of marginal products. Okay, now this is what they are showing us. Marginal rate of technical substitution we have explained, but we want to show you why it will decrease. Let us say in this information that we have here, on isocont Q2, look at that, Q2 MRTS falls from 2 to 1 to 2/3 to 1/3. So what is going on? See, so MRTS, if for the, when we make this move, the person increase labor by 1 unit, but for that they have to give us to keep output fixed, to be on the same isocont, then capital has to decrease by 2 units. See, so change in capital is 2, change in labor is 1. On the alternative, when labor increases from 2 to 3, what happens? Labor increases again by 1 unit, but now capital decreases by what? Change in capital is 1 unit. See that? So that one. We explain this. Now we explain now the next one. Again, when we go to from 3 to 4 here, what happens? Look at that, decrease in labor, the decrease in capital is 2/3. And then when we go from 4 to 5, right? This is still 1, but we are going from 4 to 5 here. So this change is what? 1/3, right? 1/3. So that is what? So that is what? Q2. That is Q2 level of output. Production functions, two special production function, two special cases. Two extreme cases of production function show the possible range of input substitution in production process. The case of perfect substitutes, the fixed proportion production function, this is one case, right? And the other case is this one, which is also called Leontief production function, after the economists who discussed them first. Now, fixed proportion production function with L-shaped isoquants, right? So that only one combination of labor and capital can be used to produce each level of output. See, then the fixed proportion production function describes situation in which methods of production are very limited. Only when factors resources are used in accordance with that method will output increased, right? So let us see here, this one, let me see. Yeah, fixed proportion is this one, fixed proportion production function. Look at that. Here we have labor on this axis, capital on this axis, Q1, Q2, Q3, those are the isoquants. Here look at that A. Only when we produce labor L1, capital K1 is output this Q1. And now if you put capital fixed and then increase labor again and again, you move on this way, right? See, you use more labor, but your output will not increase. It will remain Q1. On the other hand, similarly, if you put labor fixed here, and if you are increasing capital, right, increasing capital here, so you move on this side and output still 1. So see, this is an L shape, right? L shape. Only when we are using at that proportion will things happen. And then if you increase both capital and labor in this in the same way from L1, to look at that, to go from A to B, we have to increase capital and labor in the labor both, such that we increase both capital labor so that we can make this move. And here we are producing more. See, Q1 is what? To the right and above Q2. So at Q2 output higher than Q1. Right? Again, if you just from here, from B, if you just increase labor, output will not increase. If you just increase capital, output will not increase. They both must increase by that proportion shown by this line. If you do, then output we go from B to C, and look, Q3 higher isoquant than Q1. See that? So that is the thing. This is Leontief isoquant. What about the next one? The previous one, isoquant with inputs are perfect substitutes. Here we have labor and capital, and look, A, B, and C. See that? A, B, C. So there is what? There is perfect substitutes here. We say it doesn't matter. You can, if you reduce 1 unit of capital and increase 1 unit of labor, for example, it will keep the output fixed, Q3, right? Output will not change. So if given by the slope of this straight line, right, downward sloping straight line isoquant, increase labor again and again, every time you have to give up the same amount of what? The same amount of capital, right? You see, every time, so that is not changing. MRTS, remember MRTS we discussed last time, is here is what? Fixed, it will not change. And it's, look at that, the Q2 is parallel to Q3, again the same situation, it is the same all over. So is what? So see, this is because slope of this isoquant is not changing. If you go back here, remember here we have what? Here these are what? these isochords are convex to the origin, right? As a result, any point you measure slope, this is the slope. This is the slope. And as we said, slope of the isochord, it will show us the MRTS, right? MRTS. And this is, let us say, at point A is what? Delta K delta L, right? You know that those are the two axes, L and what? And L and K. Now this is MRTS at A. Now what about MRTS? MRTS at B. Here at B, right? At B it will be what? Delta K again and delta L, right? And you see the slope is flatter. B MRTS at B is smaller than what? MRTS at A. For this is the normal shape of isoquant, right? ISOQUANT, isoquant. And this is how things are. But this is an extreme case where MRTS at any point A, B, C is the same because it is a straight line. Those are perfect substitutes. Points A, B, C represent three different capital labor combinations that generate the same output Q1 or Q3, right? Now let us discuss this. Example 6.4. Here a production function for wheat. We have food grown on large farms in the United States is usually produced with capital intensive technology. However, food can also be produced using very little capital, a hoe and a lot of labor, several people with patience and stamina to work the soil, right? This is what they used to do long ago, right? Now, most farms in the United States and Canada, where labor is relatively expensive, operate in the range of production in which the MRTS is relatively high, with a high capital to labor ratio. Whereas farms in developing countries, where labor is cheap, operate with lower MRTS and the lower capital to labor ratio. So you see, it depends on cost of resources. In US, Canada, labor is more expensive compared to the cost of labor in what? In developing countries. So based on that, producers, they want to minimize costs. See, because this is why in developing countries, they want to use more of the cheaper factor of production, which is labor, and less of the more expensive factor of production, which is capital. And in developing countries, it is the opposite, right? The exact capital labor combination to use depends on input prices, a subject that is discussed in chapter 7 when we discuss cost. So let us see. Isochords describing the production of wheat. See, so a wheat output of 13,800 bushels per year can be produced. Look at that. This is output, right? Excuse me, the red one, the red curve is the isochord. We plot labor here, capital here, right? The more capital intensive production process is shown at point A. Here we use more capital than we are using at B. Look, capital higher. Delta K is what? Minus 10. When we go from A to B, we are what? Reducing capital by 10, but increasing labor by 260. See that? Labor cheaper in developing countries, right? And now if you want to find out the marginal rate of substitution between A and B, you just divide this delta K over delta L, put a negative sign in AMRTS. Now let us see, this is what? This is minus 10 and this is 260. So minus is 10, 260 equal to what? Equal to 1 divided by 26, which is 0.04. Is that okay? 0.04, that one. Now, the next thing we want to discuss is returns to scale. Returns to scale, right? Rate at which output increases as inputs are increased proportionately, right? So this is what this returns to scale will tell us how our the rule that is governing output, change in output to change in input in the long run when all capital and labor is flexible, right? So returns to scale tell us how output Q will change when capital and labor both increase by the same proportion. See? So increasing returns to scale tell us that suppose we increase capital and labor by a proportion K, right? No, a proportion H, a proportion H, then how will output respond? Will output also increase by proportion H or more? H, if this output increases by more than H, right? Output increases by more than H, so we call that increasing returns to scale. So let us try another way, define it. If capital and labor both double, right? Double. Use of capital and labor increase by 100%, double. Will if then output, if output increases more than double, we have increasing returns to scale. If output also double, right? Situation in which output doubles when all inputs are doubled, we call that constant. And decreasing situation in which output less than doubles when all inputs are doubled, we call that what? We call that decreasing. See, capital labor, the capital increases to K, labor increases to L, but output does not. Output is what? Output does not double. That is what? Decreasing returns to scale. So this is another way to show you. So look at that. Here we are increasing labor here, capital here, labor here, capital here, right? And then labor hours. So we are increasing what? Labor from 5 to 10, 10 to 15. And as a result, labor is increasing, doubled, right? 5 to 10 is increasing, and what happens? So from 10 to 20, this is what output is doubling. When a farm's production process exhibits constant returns to scale as shown by a movement along line OA in part A, along line OA in part A, the isochords are generally spaced as output increases proportionally. See, output increases, look at that, these are what? Proportional increase. Right, so labor increases from 10 to 15, and then 4 to 6, output increases 10 to what? 30, right? Okay. On the other hand, here in this graph, we have what? If, however, when there is increasing returns to scale as shown in B, here, this B, the isochords move closer together as inputs are increased along the line. So if output double from 10 to 5 to 10, capital goes from what? Labor increases 5 to 10, capital increases 2 to 4. What happened? Then output will increase more than double, 10 to 30, or even more than that. You see, that 30 isochord is below this line. This is where we reach. So even more than that. So excuse me. So this is how now we know that output increase by more than the percent proportionate increase in the factors in labor and capital. So this is increasing returns to scale. This is constant returns to scale. And for decreasing returns to scale, you will see the isochords will be spread further apart. So even if capital and labor increase, right? So even if capital and labor increase, what happens? Here we have 1, and then capital 5, labor is what? Capital is 2, labor is 5, and then this one goes to 10, this one goes to 4, right? 4, but what happens? But you'll see that isochord, this is output is 10, and here output will be what? Just 12. See, when labor double, capital also double, output does not double, it just goes from 10 to 12, right? That will be the case. So the isocons will be further spread. It will not be in a short, very short like that. It will be widely spread. It will take a lot of increase in labor and capital to increase output. That is diminishing, that is what? Decreasing returns to scale. Now what about, so this is how they have described, right? We have already discussed this. Now the carpet industry, you can see that. This is a recent example, right? So innovations have reduced cost and greatly increased carpet production in carpet industry. Innovation along with competition have worked together to reduce real price of carpet. Carpet production is capital intensive, means that you need a lot of machine tools, equipments. Over time, the major carpet manufacturers have increased the scale of their operations by putting larger and more efficient tufting machines into larger plants. So you see technological changes going on. At the same time, the use of labor in these plants has also increased significantly. The result, proportional increase in input have resulted in more than proportional increase in output for these larger plants, right? So what happens? Now we know, excuse me, so this is increasing returns to scale. And as we see in the carpet industry. Okay, thank you.